All right, let's continue. Let's start with step number 1. Okay, how do we know the value of VP in terms of dB, RC, and RP?
Since we have no value, this is just going to be an expression, right? Where VP is equal to like
Correct.
RC over VB plus RD over VP or something like that.
Yes, it's if you notice, VP is the voltage dropped across this resistance, that's across this node, which is simply a voltage division. You can think of this as a voltage source, okay, connected to RC and RP. Okay, and this is ground, by the way. I may have forgotten to clarify that part. The When I show this symbol right here, that simply means ground or zero voltage. Okay, that's my reference node in this circuit. Okay, so I can pretty much safely ignore this guy because there's no current going in there. Okay, so it's equivalent to finding the voltage VP is the voltage across this resistance RP, which is simply a voltage division between VP and RC. So VP would be the applied voltage VB times RP over the total resistance RP plus. I should have said RD, right? This guy is RD. RD over RD plus RC. Let's say voltage division, simple voltage division. So that's the first step done. Okay, let's see if we can do step number 2, which is straightforward. Step 1. Step number 2 says Vn is Vp. So Vp is Vn, right? This guy. Okay, Vp is Vn. So I have an expression for Vp and Vn as well. Okay, now it comes down to applying KCL at this node. Okay, step 3 is KCL at node En, which is that guy. Okay, so the current coming in, In or Ia, sorry, that's the current coming in, this guy, should equal the current leaving, Ib plus In. Okay, what's the current coming in? That's the voltage across this potential minus this terminal over the resistance over there. Okay, so it will be VA minus Vn over Ra would equal the current leaving in this branch. Okay, that branch would be voltage here minus voltage there over Rv. So it will be Vn minus Vo by Rb. Okay, once you massage this equation, we can plug in Vn equals to Vp. We know Vp is equals to Vb times Rb, Rd over Rc plus Rd. Okay, that's the value we got from earlier. Okay, so plug in those um, terms, expressions, Vn to be this guy. Okay, Vn to be that guy. Okay, and manipulate this algebraically, we get exactly what we were after. Okay, we'll get that expression. So once we plug that in to the value of Vn, we get what we were after, this guy. Okay, Vb times RD by RD plus RC into 1 plus RB by RA plus VA times negative RB over RA. Okay? Questions, please.
So just to be sure, after we plug VN and simplify, we should get what you were just showing us there at the bottom?
Yes.
Okay.
Okay. Let me write it out. V out is going to be VA times negative RB over RA plus VB times RD over RD plus RC times 1 plus RB over RA. Okay, this is the output that you should expect to see once you plug in Vn is that expression, and then simplify. Okay, can you intuitively make sense of this final result? Okay, this guy. Can you think about the intuition that this equation provides? When you look at that in relationship, when you look at that in along with the figure above, especially look at this guy. What is this weird number over here? VB is multiplied by some grotesque looking, extremely complicated looking term over there. What do you think this is this represents?
Oh wait, are you asking about the far right side of this? Yeah, okay.
Yes, this guy. Think about this. This term 1 plus RB over RA, what does that represent?
That'd be a non-inverting amp for the V out.
Non-inverting amplifier gain, right? A. And what does this term here represent? This guy.
Voltage division.
Correct. So thank you. So if you were to break it down, the whole equation, you'll see that the voltage that you applied VB, some part of it only shows up at that node VB or VP, okay? And whatever part, so this part VB times RD over RD plus RC, a small fraction of VD shows up at VP, and that is amplified by the non-inverting gain. And then VA, all of that is amplified by the familiar negative RB over RA. Okay, so that's more or less, if you don't break it down into its constituent terms, it may not be intuitive, but once we try to make sense of the intuition that these terms provide, it's much easier to remember and much easier on memory. So that's the idea. So that completes all the amplifiers that we want to look at for an OpAmp. Okay, so the different amplifier circuits. Let me go back, and in the interest of completeness, do this guy as well. Summarize the OpAmp. Okay, summary page 4. I'm going to make it quick so we can look at some problems. OpAmp summary 5. Okay, so when we have a difference amplifier, okay, the output is going to be VA times negative RB over RA plus VB times RD D plus RC times 1 plus RB over RA. Okay. That's the idea of a difference amplifier. Okay, questions please.
So in the very last op amp that we looked at, when we found VP, you had just recognized that there was basically a voltage divider there,
Yes.
and then you use the voltage division formula to solve for VP. So just had we forgotten that formula, what would be another way to solve that VP?
This guy, right? Okay. Let me see if I can add a page over here, somewhere over here. Okay. Let's see, add a page and copy this guy. Okay. Copy this guy. I'm not a very big fan of remembering equations, and it's a very good thing that you wanted to talk about this guy. So if you were to forget the expression for voltage division on this guy, you're talking about this guy, right?
Formula could be used right now.
Right? Is this the one you're talking about?
Yeah, correct.
We want to find the voltage here, which is VP. All right. How do we find VP? Well, the whole premise of voltage division is noticing that all of this, I want to call it as I total. Just some name, some random name. I'll call it I total. And the voltage VP would be the current flowing in here, I total, times RD.
Okay, so we just go right back to Ohm's law.
We go back to Ohm's law, but then we still have to find I total. How do you find I total?
Well, we'd sum the resistors, and then take the given voltage, and then we would have the two other components of Ohm's law that we would need to find the current. That's what I would generally do.
Right, exactly. So that's the total VB over the sum, the total resistance RC plus RD.
Right.
Right? Multiply that. So that's this guy, IT. And in order to find VP, I simply have to multiply that by RD. So what do we have? We don't have to remember the equation here. You simply remember that the resistance here, RD, times the total current in here, that's all of this guy, would give me the voltage drop, VP.
Perfect. Thank you.
Yeah. Other questions, please. All right, so let's see. Let's see if we can look at some problems. Okay, let's start with an easy one. Okay, let's see. Okay, OpAmp problems. I'm going to add a page here. We'll do a couple of problems. Okay. Here is an OpAmp, negative and positive configuration. Then I'm applying 10K and 5 volts over here. Okay, and 6K, 3 volts over here. Okay, and that's being fed through 3 kilo ohms. Okay, and there's a feedback resistance of 5 kilo ohms. Okay, there's a load resistance of 4 kilo ohms. Okay, this is V naught. Okay, what we want to find in this problem is VO, V output. What's that value? And once we have that value, I should be able to express IL. Okay. So why don't you take a couple of minutes to see if you can give me the value for VO, IL. Okay. Take a few minutes, maybe 5 minutes to come up with the value of VO and IL. Okay. Any volunteers to get us started? We might as well apply the formula that we saw earlier in the difference amplifier. But that's no fun in that. Let's do this step by step by finding VP. Okay, VP is going to be a voltage division. Okay, between 3 volts and 6K and 3K resistance. So that's 3K by 6K plus 3K. Okay, so that's going to be 1 volt. Okay, VP is going to be 1 volt. So step number 2 tells me that Vn is same as Vp. It's also going to be 1 volt. Now I can write KCL at node B sub n. Okay, the current coming in here will be the current going out there because there's no current IN going in here. Okay, the current coming in here would be I1, call this I2. Okay, I1 would be 5 volts minus 1 volt over 10 kilo ohms. That is equals to 1 volt. So this is Vn, right? This is V sub n. V sub n, 1 volt minus VO over 5 kilo ohms. 5 kilo ohms. Okay. So once we do that, we should see VO will come out to be negative 1 volt. Okay. We'll see that VO is going to come out to be negative 1 volt. It's easy to do that math. This is going to cancel 2 times. I'm going to be left with 4 volts. Okay, so this is going to be 4 volts over 2, which is going to come out to be 2 over here. So it gives me 2 equals to 1 minus VO. Therefore, VO is going to be negative 1 volt. Once we find VO, it should be straightforward to find IL. Okay, IL would be VO over 4 kilo ohms. That gives me a value of negative 250 microamperes. Okay, that's the idea of VO and IL. Okay, questions, please.
So when you did step 3, KCL at node, or at the negative node there,
Yes.
so you have 5 volts minus 1 volt. Now, is that because originally everything for that equation was on one side of the equal sign and then you moved it over to the other side to equate them to each other? Because I thought that when we're
Yes.
looking at Vn, it would be Vn minus 5 volts over 10K to find I1.
Yes. 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 Yes.
Okay,
So I could have done that. I could have done this guy. What you said is Vn minus 5 volts. So I'm assuming the current leaving here plus that guy equals to 0. Or like you mentioned earlier, what I have done is simply changed this direction to be 5 volts minus Vn and brought it to the other side of the equation.
okay. So both forms are valid?
Yes, both forms are valid.
Okay.
Okay. Both forms are valid and equivalent. Okay. That's a good point. Let me say that again. So if I chose the direction of current to be flowing in through this branch and flowing out through that branch, I could apply a KCL equation that says the current coming in equals to the current flowing out. Okay. On the other hand, if I did the opposite, if I chose a current direction that's going this way, and it's completely up to me, I could choose a current direction that I prefer and stick to it throughout the problem. Okay, be consistent with it. Then what I would say is I1 plus I2. The sum of currents leaving a branch is 0. Okay, both of these lead me to the same solution. Okay, so that's the idea. In this case, what I have done is I have chosen the current to be going from left to right, and therefore, if you look at that node, there's one branch current coming in and one branch current flowing out. So the heart of KCL is there is no current into the node, or there's no current at the node. So all the current that is coming in should leave. So the current coming in should equal the current flowing out. So that's the way I chose to look at it. But you might as well have chosen the opposite direction and arrived at the exact same result. Other questions, please. Okay, let's do one more problem. Let's do a little bit, a small enhanced version of this guy. Okay, problem number 2. Okay, let's still do an OpAmp with a negative configuration, negative feedback. Okay, there's that negative feedback over here. It's 180K. Okay, and this guy is being fed through 2 resistances. Okay, there's VA, there's VB over here. The resistance values here are 20 kilo ohms, 18 kilo ohms. So far this appears something similar to the summing amplifier that we saw. Okay, in addition to that, there is this guy as well. Okay, there is a resistance down here, 20 kilo ohms. Okay, and there is one guy, 20 kilo ohms, that is being fed through VD. Okay, and there's a 30 kilo ohms. It's being fed through VC. Okay, so what we want to do is to be able to calculate a value for VO. If I give you the value of VA to be 1 volt, VB to be 2 volts, VC to be 3 volts, and VD to be 4 volts. So the question is, what is the value for VO? Okay, take about 5 minutes to work on that. Okay. All right, let's see if we can begin here. Any volunteers to get us started? Let's do this problem your way, any which way that you want to choose the current direction, writing the equation, so on and so forth. I want you to drive the discussion here. So the first step is to write. It seems there are 2 sources here, VC and VD. Like we discussed earlier, the first step would be to find VP and equate that to Vn, and then write a KCL over there at Vn, right? But it seems in order to be able to find Vp here, we should first write a KCL at node Vp. So this is the first of its kind where Vp is not readily obvious. We have to kind of go through a little bit of exercise to find that. All right, any volunteers to get us started with KCL at node Vp? In order to do that, you have to choose current directions in this resistance and in this resistance. Okay, so tell me, and also of course this resistance here. If you think about it, there's only one way in which the current can flow in this resistance, but you don't have to assume that direction. Okay, you can choose any direction that you want to choose. So tell me, what direction do you want to choose for the currents in the 30 kilo ohm resistance, the 20 kilo ohm resistance, and another 20 kilo ohm resistance here? Okay, you guys can hear me, right?
Yes, we can hear you.
Okay, do you guys want to start off by giving me a direction?
Sure. I would suppose we can have the directions of the current from the VC and VD going towards VP.
Like so?
Yep.
Okay, I'll call that IC. Tyler, thank you.
Yes, sir.
VD is this guy. ID is the direction, that's the direction you chose. How about the current in this resistance, 20 ohms, 20 kilo ohms?
I suppose for the sake of having everything go in the same direction, let's just have it go towards VP as well.
That's going to VP as in this way?
Yeah, sure.
Okay, so how about, let's not forget this guy, this current over here. What's that guy?
That should be 0.
That's 0, right?
Yeah.
So now the observation that we want to make is
That
the
everything going
VP
into the node is.
correct.
Sorry, go ahead.
This node is exactly the same as this node, is exactly the same as this node. So all of these, even though I have shown them using 3 different nodes, they're still representing the same potential because there is no element, circuit element, resistance or capacitance, nothing in between them. So all the 3 nodes here shown in black are exactly at the same potential VP. Okay, so let's get started with the KCL at node VP. Okay, so the voltage here is VP as well. So the currents leaving this node through IC would be VC minus VP over 30 kilo ohms. Okay, similarly, VD would be, or ID really would be BD minus VP over 20 kilo ohms. Let's name this current here I E. Okay, so IE, that's the current going up. That guy is 0. So if you think about it, this potential minus this potential, 0 minus that potential over the 20 kilo ohm resistance. Okay, so IE is this guy. So when I'm applying KCL, I can apply it in a bunch of different ways. I can say the sum of all currents leaving equals to 0. Or I could even say sum of all currents entering is 0. Okay, in this case, there are 3 currents entering IC, ID, and IE. Okay, IC, ID, and IE. So if I do that, IC plus ID plus IE equals to 0. Right? Everybody with me?
Yeah.
Okay, so VC minus VP over 30 kilo ohms plus VD minus VP over 20 kilo ohms. Okay, this guy is kilo ohms. plus 0 minus Vp over 20 kilo ohms. All of that equals to 0. Okay? That is KCL, sum of all the currents. Okay. Now what I do is I manipulate the equation. Let's see something in the chat window. Okay. Let's see. If we manipulate the equation, we're going to get something like, it's just a matter of massaging the equations now. Expressing Vp in terms of Vc and Vd. Okay. You should get something that looks like 1 over 4 Vc plus 3 over 8 Vd. Okay.
Professor, just one small question.
Yes.
For the KCL, wouldn't it basically IC, ID, and IE equal all be negative because it's going towards the VP? So shouldn't the equation be flipped, making it be VP minus VC over 30 kilo ohms?
Sure. So you want to do, see the reason, the direction I chose this guy is, all I have done is, when the current is going from left to right, I express it as the voltage on the left minus voltage on the right by 30 kilo ohms.
Yes.
Okay, so give me 1 second. We'll flip these equations. Okay, we'll flip these equations and see how the problem comes out to be exactly the same. Okay, let me copy that. So this is the expression that you would get for KCL at node VP. Okay, that's the node right here, VP, this guy. Okay. Now let's see, in order to clear this up, okay, it seems the more we look at it, the better. Okay. So Tyler wanted to choose the current directions in the fashion that we use now. Okay, but now you want to do a different direction. Okay, you want to do this guy, right? So why don't you pick the current direction for me?
So basically I did the exact same thing, but I just did it the other direction, going toward away from VP.
Okay, how about IE?
As well, we're going away from VP.
Like so?
Yes.
Okay, here, when I apply KCL, it's going to come out as currents leaving the node VP. Sum of all of that goes to 0. Okay, if you were to look at this guy, I'm sure you must have got VP minus VC over 30 kilo ohms for IC, right?
Yes. Basically, the whole equation you got by basically just the VP or the VD flipped.
Yes, just about everything flipped here. So what I could do is look at what I'm going to do here. I'm going to multiply the left hand side by -1 and the right hand side by -1.
Oh, and then it
Okay,
just basically flips.
it simply flips. And then the right hand side is still going to be 0. So there is an equivalence. When you choose the current directions and are careful with setting up the equations,
Got
then
it.
the equation does not matter.
Okay, making sure.
Okay, that's a very good question. Okay, it'll come out to be exactly the same as before. It'll give me the exact same result. Okay, copy that, and I'm going to paste it over here. Okay, so VP is coming out to be that guy. Now that's all step 1, right? Step 1 is find VP by writing KCL. Now step 2, VP equals to VN. Okay, because of virtual short. Okay, VP will exactly equal the voltage VN over here. Okay, VN is going to be that guy. Now we can go to step number 3, KCL at node Vn. KCL at node Vn. So in this branch, what I could do is I could look at the currents leaving. Okay, this is what Professor Tatro does. Right? He looks at all the currents leaving a node and he sums them to 0. Okay, I can call this as IA. I'll call this as IB. We'll call this as IO for output. And then let's not forget the little IN here, which is 0 anyways. Okay, that guy is equals to 0. Okay, so when we write the KCL at node Vn, it's going to come out to appear like IA plus IB plus IO, all of that equals 0. Okay, KCL at node Vn. Once you do that, okay, it's just a matter of plugging in the appropriate terms in there, and what you'll get is 20 Vn minus 9 times Va, okay, minus 10 times Vb, all of that equals to Vo, okay, V output. So this is from step 3. So all of this is from step number 3. So this next step I'm going to do is to plug Vn. In place of Vn, I'm going to plug this guy. Okay, all of that. So Vn equals to 1/4 Vc plus 3/8 Vd. Okay, we could do that, and then once we plug in all the terms, okay, and plug in the values, Va equals to 1, Vb equals to 2, Vc equals to 3, and Vd equals to 4. You should see then you have no unknown. You have a value, you need a value for Vo, okay? You're after a value, not an expression. But then you have Va to be 1 volt. You have Vb to be 2 volts. You don't have Vn, but there's a way for you to find out from Vc. This guy is 3 volts and Vd is 4 volts. So you have all the terms known. It's a matter of finding out, plugging in the numbers and finding out a value. Vo, did anybody go to that step of finding the final value for Vo? It's just a matter of calculations. So I'm going to give you the term, the value that you should expect. So you can work on this at a later time if you want to plug in the numbers and see if you indeed get this answer, 16 volts.
So then, just to be sure, we replace Vn with the Vp that we found because they're equal. And then we just plug in the given values for the different voltages in that formula there and calculate it and figure out what Vo is. Perfect.
Okay. All right, other questions, please. Other questions? All right, let's do one more problem. This might appear simple given the fact that, just give me a second. Sorry. All right, so let's do one more problem, problem number 3.
So are these the types of problems we should expect on the Am for the OpAmp section?
Yes, you can get started with the homework actually to see if there are different questions. And if you have some questions, you're always welcome to send me an email.
Alrighty.
But then this is more or less the kind of problems that you should expect on the homework and also the exam. And importantly, even if the problems are different, if you're equipped with the tools that you need, like step number 1, virtual ground, step number 2, input resistance is infinity, I'm sure you have the technical wherewithal to solve any kind of problems that you encounter in the exam. So don't be thrown off, don't be deterred if you don't see the exact same problem. You do have the wherewithal, technical wherewithal necessary to solve any kind of problems, even though they may appear to be different. Okay, so let's do one more problem. Okay, this guy.
So these 3 steps that you're giving then, those are 3 steps that should be able to be utilized on any of these OpAmp problems.
Yes, correct.
Okay. Okay.
So generic steps. So let's do one more problem. We'll do this problem and call it today. Okay. Plus minus 2 volts. Okay. There is a little bit of there. So this is a negative terminal. This is a positive terminal. So there is that VO, V output. Okay. Let's see. 10 kilo ohms, 20 kilo ohms. I'm interested in finding out V output. Let me give the polarity properly. This guy is positive. This guy is negative. Okay. I want you to find V out. Okay. So take a few minutes to solve this problem and find the value of V out. All right, let's get started with this problem. What's the value of VP? Something in the chat. Okay.
Is it just 2 volts?
VP is 2 volts, correct. Tyler has the right answer. Tyler, you have the right answer. What's VN then? That's equals to VP as well. So that's going to be 2 volts, right? Now let's apply KCL at node VN. So I don't know, I want to call this as IX. And I'll call this as IO. Okay. So IX plus IO should sum to 0. Okay. IX is what? VN, which is 2 volts, minus 0 over 10K plus 2 volts minus V output over 20K. Okay. That's each of these represents the current IX. That's this guy. And IO, that's this guy. And all of that should equal 0. You massage this equation. V out should come out to be, like Tyler said, 6 volts. Okay. There's a different way to solve this problem by noticing that this is a non-inverting amplifier. See, I'm applying, okay, let's see. So this is virtual ground. Okay. And then I implicitly notice the fact that IN equals to 0 when I'm doing KCL. Okay. So the idea is that I could have solved this problem by using this formula, V output. This is a non-inverting amplifier because the input is applied to the positive terminal. Then there is a negative feedback. Okay. By noticing that this is a non-inverting amplifier, V output is going to be VB times 1 plus RF over RA. Okay, that's RF, right? This is RA, right? So this is 1 plus RF over RA. Okay, this ratio, all of this is going to be 2. 2 plus 1 is 3. 3 times VB, 3 times this guy, this is VB. Okay, so V output equals to VB times RF over RA. Okay, we would have arrived at the exact same solution as well. Okay,
How would we have differentiated between RF and RA? Because it would be different had we flipped the 10K and the 20K.
as in, let's say, let me clean this up and then I'll come back. Well, the idea is whatever resistance is tying the V output back to the VN node, that's what is contributing to the feedback, right? So this RA, so my understanding is that when you're looking at the non-inverting configuration, let me go back here. Let me go back all the way to the non-inverting configuration. That's right here, right? There is one resistance that ties the output back to the negative terminal. That's RF, feedback resistance.
And then
Okay?
one to ground.
One that goes to ground. That's RA or RS. Okay, so by that logic, what I have done here is that the resistance that is tying the output back to the negative terminal, I call that RF. And the one that's going to the ground is RS or RA.
Perfect. Thank you.
Yes. Other questions, please.
So that equation only works when only one voltage supply is applied, right? Like if there is another voltage supply on the negative terminal, we would have to use the node or KCL.
We would have to use the KCL, or we could use this guy. Okay, let me go back here. The difference amplifier that we looked at. Remember, you were talking about something like this, right?
Yes.
So we looked at the difference amplifier where VB behaves like a non-inverting case. The red one is amplified positive, and the blue input applied to the negative terminal is going to be amplified using an inverting configuration. So it's a combination of inverting and non-inverting, which we already derived to be a difference amplifier.
Okay,
Does that
thank you.
answer your question?
Yes.
Other questions, please. Okay, so we kind of looked at all the configurations possible. What happens if I completely grounded the positive input terminal and applied a bunch of inputs on the negative terminal? Okay, we looked at that. Let's see, in terms of the difference amplifier, see, I ground the positive terminal and apply more than one to the inputs. Okay, so we looked at the different configurations possible, and you're free to entertain, you're free to exercise your creativity and come up with different configurations and solve them by yourself. But we looked at the major representative cases. Okay, so what I want to do is to stop here, unless you have questions, and then we'll come back to solve this. We'll come back to work on, we'll do chapter number 6. So this will be the end of chapter number 5, operational amplifiers. When we come back, we'll be talking about chapter 6. Okay.
So will we be doing chapter 6 tomorrow as well as Monday, and then the exam is on Tuesday, or are we covering all of chapter 6 tomorrow?
Well, I don't have anything set in mind. So if we finish chapter 6, all of chapter 6 to my satisfaction tomorrow, we'll not come back on Monday. But if I feel that, if you feel that we need a little bit more practice, we can come back on Monday. If not, we can take a break on Monday. That really depends on how you feel about chapter 6 after looking at it.
Is there any chance we can do on Monday? Is there any chance that we can do a small review before the exam?
Sure, we can do a review on Monday. If we have, I think with that in mind, I'm going to try to cover as much of chapter 6 as possible tomorrow, and then reserve some time for a quick review.
Yeah, that would be awesome.
Absolutely, not a problem. Other questions, please? All right, let's stop there, and I'll see you folks tomorrow.
All righty. Thank you. Have a nice day.
Thank you, Professor.
Take care.